Okay, so welcome to the session. We are looking at tutorial 4 here, and we're looking at root locus diagrams. So just as a reminder, in the last session, we were looking at our linear systems of equations like this. So our linear system had a constant times y, and then plus some control function here. So we were taking some control action, and usually that's something like a flow rate. And I think we made the point before that in chemical engineering, that's how we apply all our controls, right? We have some flow rate to our system, so it's an inlet flow rate, or it's generally with inlet flow rates that we control our processes in chemical engineering. So we have some control variable here, or some manipulated variable, and we are trying to control some output variable y, which might be a concentration or a temperature or a pressure. So whatever it is, for a linear system of equations, we'll have some constant times the state variables y, and we'll have some unspecified time function. So at least in the last session, u of t was some unspecified function. So that was just a step function or a sine wave function. So we gave ourselves the freedom up to now to just prescribe that time function. So that was what we did in the previous tutorials, right? And we also showed that for that time function, we could convert that into the Laplace domain, and we could rewrite it in the form the Laplace version of the state variable times some transfer function times our input, our manipulated variables transfer version. And so we looked at some responses there. So in this section, we are looking at closing that loop now. So instead of saying that u is some unspecified time function, we are now going to create a u function which will help us accomplish our goal in control. So in control, we want to specify some set point for our state. So like we said, y might be a temperature or a concentration. And we know in our process to get this reaction rate in the reactor, we need this temperature and this concentration. So we know what value we want that reactor to reach. So we want to specify some set point value for y. And we'll define that as YSP, Y set point. Yeah, and just be careful of notation collision. I used a subscript S for steady state last time. From now on, SP, that's our set point value. And you can see here that this, this proposal for a controlled time function would make sense to us, right? We want to control our process. We want to apply an input, an inlet flow rate, for example. We want to apply something which is proportional to the difference between the intended set point and our current state. So if let's say it was temperature we were trying to control. So we currently have some temperature T in the reactor, and we wanted to reach some other temperature TSP. So the difference between those two, let's say our current temperature was 300 and we wanted to reach 400. So the difference of 100 should be proportional to the amount of control action we need to take. So for instance, if it's a high pressure steam, then we want to use steam in proportion to that difference. Let's look at the other side of it. When our system reaches that temperature, let's say we manage to get from 300 to 400, then it's not necessary to use more steam. We can say that process now has the momentum to stay close to that value. And so we don't want to use additional steam once we reach the set point. So as our process reaches the set point, we want to take less control action. So does that make sense to you? Does it make sense that we are proposing a time function like this? And so our control action is proportional to the difference we are, how far away we are from the set point. Okay, so that's what we are trying to do now. We are going to close the loop. So before this was an unspecified time function, we are now going to specify this in terms of the intended control action. Right, so that's now our function. And we recognize that if we make such a proposal, that's going to change how the transfer function is going to look to us. So we know that when we had converted into the Laplace domain, so last time we'd done all that work when we had our model, we showed eventually we could write it in this form: y is equal to gp times u. So now if u is a function of this difference, right, the set point minus the current value, then we can say that if we Laplace transform this, we are going to get capital U. And then for the function, that's going to be a controller transfer function. And that will be a function of this difference. So YSP, we can write as capital YSP, and minus Y in the Laplace domain is a capital Y here. So the controller, we've used proportional. This is so-called proportional control. So in this case, we just said some constant multiplied by this difference between the set point and the current value. That's not the only possibility for applying control. And you'll have seen already the proportional integral and the proportional integral derivative controllers. So you have other types of controllers, but they are all based on this difference. So they are all some function of the set point value minus the current value. So for the proportional controller, it's a constant times that difference. So here we are writing this a little more generally. We are saying we will have some transfer function for the controller, and then we'll be multiplying by YSP minus Y. And so the controller itself will have its own transfer function, right? We've shown up to now that the process has a transfer function. So you've got a reactor and you've got reaction, and that's influencing your process, or you've got a heat exchanger and there's a certain rate at which heat is transferred between the shell and the tube and all those things. So that all reflects the physics of the problem. And then we are adding control on top of that. So we are controlling how fast the valve is turning in response to what's happening. So there's a different set of dynamics there. So we will summarize all that in GC, so the controller's transfer function here. All right, so we have this form now, and we can see we've got y on both sides of this equation. So we can bring this y across here, and we can rewrite it as y times 1 plus GPGC. And then left over on this side is this form. And so we can say that y is equal to GPGC over 1 plus GPGC times YSP. So if you like, this is the new controller or the new process function. So now we are influenced by the controller, where the controller is this time based on the difference between the set point and the current value. So when we do that, we no longer just have GP. Right? If you look in tutorial 3, we always had y equals gp times u. Now that we've specified a form for u like this, we can say that y is equal to gpgc over 1 plus gpgc times ysp. So that's the new form that we are working with now, which is just a consequence of specifying this. Okay. I can pause there. Any questions or comments there? Okay, if not, so that's the form that we have now. And like we said last time, the poles of the transfer function, in other words, the values of s, where the function goes to infinity. So the poles of our transfer function, those turn out to be the time constants in our process. So in other words, if we look up the values that make the denominator of this transfer function 0, then those will tell us how the process is going to behave. So we just look up the zeros of this denominator. So we find the values of S of 1 plus GPGC, and the solutions we get here are going to be the time constants. And that's where you should look back at tutorial 3, and we'll see there that any of those poles, those turned out to be in the exponential. So we had that explanation last time. Our final solution is going to look like y equals something times e to the kt, and k was the solution to this here. So k was the value which made this go to infinity. So if we just find the roots of this denominator, the roots of that denominator will give us the time constant of the solution, and that's going to tell us how the system will behave. And like we said last time, if any time constant has a positive real part, then the solution will shoot off to infinity. If we have any imaginary part, that's going to cause oscillations. And so those are the things we will use to investigate how best to create this control. Now, in this case, when we implement our controller, that's going to show up in GC in terms of Kp, tau I, and tau d. So let's not worry about tau I and tau d as yet. In this example, we've been talking about proportional control. So our GC looks like this basically. So it's Kp. So in the case of proportional control, GC is just Kp, so it's just a constant. So in our solution, we are going to get this constant Kp, and we want to know what values of Kp will help us stay stable. So are there values for Kp which are going to cause our system to shoot off to infinity? Are there values which will make it oscillate and so on? So we'll look at all that in the context of an example now. Yeah, I think let's come back to this. Let's start with the example, and we'll come back to the rest of these notes here. So let's say in this question 1 of tutorial 4, we have a process that has this first order decay, right? So the process itself, dy dt equals minus 5y, right? So we know that this is an exponential decay. And if you solve that, right? So ignoring the controls part, let's say for now we didn't have a u variable to control. Let's say we just had dy dt is minus 5y. Then if we solve that, we can say that we have y equals y naught e to the minus 5t. So that means as t goes to infinity, this term will get closer and closer to 0. And so left on its own, this process is just going to zero out, right? It's just going to start from whatever initial value it started from. In this case, it was a 2, and it will just slowly die out. And in the question, we say here that, yes, the initial value is 2, but we want to maintain this process at a value of 3. So we don't want y to die down to 0. We want y to stay up at a 3. And we are doing that by applying some control action. So for example, if this was a batch reactor and y was concentration of component A, and A was being consumed, then of course A is just going to die out eventually. So now if we don't want A to die out, if let's say A was the primary reactant and we want to maintain a good concentration of A, then we might turn it into a semi-batch reactor, and we might be pumping A into that reactor. And so we say, well, we might start at 2, but we want to stay up at 3 because it gives us a nice reaction rate. So we want to know, how do we convert this U into a nice control action so that we maintain this value of 3. So in the solution here, we are saying, yes, without control, that's what's going to happen. And let's do what we did last time. So just for, I guess, completeness and to make that connection with what we were doing last time, let's introduce the deviation variables. So assuming we were at steady state to begin with, we can set the steady value to 2. And so we can work out if initially we were at 2, then from the equation, if we go back to, if that's our equation, then the initial value of u here, we can find by saying initially if we were at steady state, that's a 0, and then we can solve out, and we can show that the initial value of u was a 10, right? So we can write that in here. We can say minus 5y plus u, if we say plus 10 and minus 10, just to add a 0. And then we can group in here y minus 2. And then we can rewrite this as u minus 10. Then we can say our deviation variable y minus its steady state value is y dashed, and u minus its steady state value is u dashed. And so now we have the deviation form of the equation. And we Laplace transform this. So this becomes sy, this becomes minus 5y, and this becomes a capital U. And now, we group then the y here. So that's s plus 5 equals u. And so that's our transfer function. So without as yet specifying a form for u, so for the process itself, that's the transfer function. So we have a first order decay with a time constant of 5, and you can see you get 1 over s plus 5 as a result there. Now, if we go ahead and say, well, we don't want u to be some arbitrary time function, we are going to try to reach this value of 3. We want a steady state value of 3, and we'll try to reach it by applying u equals kp. So we'll implement proportional control. So applying proportional control, we can say in the Laplace domain, it's going to be capital U kp ysp minus capital Y. And here's just a comment that actually ysp is, remember, ysp is a constant. So it's actually a constant over s when you Laplace transform. But anyway, we will just accept that this is a ysp. That is the function capital ysp. It's actually a lowercase ysp over s. So anyway, we just accept that's the function that actually applies. Any questions or comments so far? Okay, so we can go back here. We said y is s plus 5, and now we have a form for u. So we can just substitute this u function here. And then we notice we again have y on both sides of this equation. And so we can group out this y again. And so we can rewrite it in this form. Let's see, I seem to have written it slightly differently here. Yeah, so here, instead of grouping, what I've done here is just noticed that this s plus 5 is the same as 1 over gp. So s plus 5 is 1 over gp from here. And so you can also just rewrite it like this. So this is a little bit more general. And you can multiply the gp across there and then group out the y. So we bring y across here. So it's 1 plus gp kp, and then left over on this side is, there's a gp missing here, right? Yeah, so please make this correction. Yeah, I'll change this in the notes, but there's a gp missing here. So anyway, and here then as well. So we can say now that y over ysp, so if we just divide both sides by ysp, and then you take this across onto the other side, it's kpgp over 1 plus kpgp, right? So that's now the so-called open loop transfer function. So that's the form that we get for our first order process that's controlled by a proportional controller. And like we said, the roots of the denominator are going to be the time constants of the solution. So the roots of the denominator are, of course, the solution to 1 plus GPKP. And so we can rewrite this. So we can, in the context of the example we are looking at, we can substitute for GP, which is 1 over s plus 5. And so we can multiply both sides by s plus 5. And so we'll get here s plus 5 plus kp equals 0. And so we can say s equals minus kp minus 5. And so this tells us then that we will have, that as we vary kp, we will vary our s value. So the root changes in direct proportion to kp. And so as kp becomes larger, s becomes more negative. The smallest value of s is when kp is, the largest value of s is when kp is 0. And so that's going to be minus 5. So minus real, it's a real number and it's negative. So that's nice and stable. And there are no imaginary parts here, so no oscillation is possible. And as we increase kp, it only gets more negative, and it doesn't ever become imaginary. So for this problem of a first order decay, we will always have stable, non-oscillating solutions. And you might find this abstract, right? So I fully acknowledge this looks unfamiliar in this form. So let's make it more familiar to ourselves. Let's go back to the time domain and apply this control. And remember, there's nothing to stop us ever doing that. We can always go to the time domain and we can simulate what would happen if we apply this kind of control. So I'm going to do that here. So I'm going to do that using using this Python code. So we have this process, right? It's basically minus 5. So here, remember tau is minus 5. So it's minus 5 times y plus u. So that's our equation. And we are applying a control action kp times ysp minus y, right? And of course, you have access to this notebook, so you can read the details and confirm that this is the same form of the equation. So what we're doing now is just simulating this, this differential equation. Yeah, and I see, let's just write out what we are doing here. So we are taking dy dt equals minus 5y plus u, and u is equal to kp times y minus y sp. And in our case, we want to reach a value of 3, right? So our set point value is 3. So yes, we can do all this Laplace domain investigation, but there's nothing ever to stop us going to the time domain problem and looking this up, because this we understand very well, right? In the time domain, we have real things like concentrations and temperatures and so on. So we can always go back to the time domain version of the problem and look at, if we apply some kp value here, how is that system going to respond? So let's set that up here so you can see the time constant set up. And I'm going to switch off control to begin with, right? So let's set Kp equals 0, and let's integrate. So we are integrating from t equals 0 to 2, and this is what we get. So remember, we said the process starts at a value of 2, and in the absence of control, so if we don't apply any control to this process, then the process will just die out, right? We said it will start at 2 and decay slowly down to a 0, right? Now we want to reach a value of 3. So let's apply a lot of control. So let's say we use a high value for Kp of 1,000. And let's just think about what should happen. We can see here that we are going to get 1,000 times the difference between the set point value and y. Right? Our set point is 3. That's what we want to reach. And if y is below 3, then this is going to give us a large positive number. So that's going to basically force in a high concentration of component A. So it will start flood. If that's the reactor, we talked about it a little bit as a reactor, as a batch reactor going to semi-batch. So if we start flooding that reactor with component A, then the concentration will rise, and then as we get closer to a value of 3, this becomes smaller, and then and so the process then regulates to that value of 3. So let's run it like this. And so you can see here we started at 2. This time it goes up to 3 and stays there. So even if the process tends to run over that, so even if we momentarily rise above the 3, right? If we are above 3, let's say y somehow goes to 4, then it becomes 3 minus 4, and then that's a negative flow. So we don't really plan to do this, but we could look at withdrawing also. So instead of feeding in, we could be drawing out of the reactor, although that's not really what we do. But anyway, that's what can happen here, right? So it controls up to a value of 3. Now that's applying a Kp value of 1,000. Let's drop this value. So if we drop Kp down to a 1 here, then you see we don't reach a value of 3, right? Our value doesn't go down to 0. It's some non-zero value. You can see 0.8, 0.6. Maybe this is around 0.5. It seems we reach a new steady state, which is not 0, but it's not 3 either. So when Kp is too low, we will never reach that intended set point. Let's try a 10. So now it actually stays on a value of 2. In other words, the consumption of A in terms of that minus 5, right? Remember, our equation looks like this. So y is being consumed here. So minus 5y, we are losing y over each time unit. So we are losing y here, and then we are gaining y from this term. So if we set Kp equals 10, that actually perfectly balances it, and we just stay on that fixed value. So we won't reach our intended steady state for Kp equals 10 either. Let's try 50. So it goes up, but it doesn't go up to a perfect 3 either. We reach some other steady state. And then as we go to arbitrarily large values of Kp, let's use even 50,000, then you see we get to a value of 3. So just saying that we implement control doesn't automatically mean that we are going to reach that steady state value, right? We are going, or it doesn't automatically mean we are going to reach the intended set point. So implementing control means that we do have to tune that controller as well. So the constant behind that controller, that Kp value, we have to find values of Kp that accomplished the intended goal, right? Any questions or comments so far? Yeah. So, in fact, there's another version of this problem. Let's say this wasn't a first order lag, right? So let's say the problem wasn't minus 5y. Let's say instead the problem was plus 5y. So that's part B of question 1, right? Let's just call this y2. So let's say we had a different version of this problem, which was 5y. Right now, this problem tends to run away. You can see, even if you have a small value of y2 to begin with, let's say your initial value was 1, then as time goes on, after 1 second, in fact, 5 times 1 is 5. So this is a positive, your gradient is positive, so y is going to increase. And then 1 second later, it's going to be a value of, what was the initial 2? So 2 plus 5 is 7. So 1 second later, the value is 7. Then it's 5 times 7, which is 35. So then y will increase up to 35 plus 7. And then 1 second later, you can see it's going to exponentially explode away from you. So when we have a positive here, this is going to run away. And in fact, that was a question that was asked last time. I can't remember. I think maybe Jenna, you asked the question, what about processes which have instability in them? So this is an example of an unstable process, right? The first one was stable. That was just zeroing out, right? It was undesirable, but we don't think of it as unstable. It's not running away to infinity. This second problem with the positive 5, that is an unstable process. That's going off to infinity. And here we are trying to control that with the same proportional controller. So here we are applying proportional control, and we are trying to get the system down to this value of 3. And let's see if we can do that. So now instead of our constant being minus 5, it's a plus 5. And let's not use any control to begin with, and let's see what this does. So here you can see if you don't use control, this process is going to run away. And even after 2 seconds, it's gone up to 40,000. And of course, if we increase the time range there, then as t increases, this goes off to infinity, right? So this process is inherently unstable. Now, if we apply control, so let's say we use a value of kp of 1,000, you can see here it goes up to 3 and it stays on 3, right? And that's because we are now removing material from the reactor. So the tendency for y2 is to go far above a 3, but the moment it goes above 3, then this term kicks in. So if y2, if y2 goes over 3, actually, I think it's the other way around. I think it's 3 minus y2. Let's just check here. Yeah, it's y sp minus y. That's what I've been using. So I wrote the wrong thing in here. So it's 3 minus y. 3 minus y. So when y2 goes above 3, then we get to negative. Let's say y2 was 4. So this is a minus 1, and kp is 1,000, so it's a minus 1,000. So it's going to push the value of y down again. And then when the value goes to around 3, then this becomes a 0, and we get no further contribution from this term. So you see the same controller is accomplishing the same effect, whether it's tending to exponentially decay or to explode away. Right? It's going to bring us to that value of 3. whether or not we will get to that steady state value does depend on the value of Kp that we use. So if we use a 1 here for this exploding problem, you'll see it still explodes. In other words, here Kp is not high enough for us to contain this, this system. So we have to use a higher value of Kp to limit the explosion and to avoid the explosion. And here again, you can see that the Kp value does change the steady state of the process. It's not on a perfect 3, because at this stage where Kp is only 100, it's not enough for the steady increase, right? You can think of this as a constant increase in Y2. So this is strong enough to cause the process to rise constantly. And here, when you don't use a high enough Kp, this isn't strong enough, this isn't high enough to overcome that momentary increase. You can think of that as the momentary increase in Y2. Any questions or comments there? So the takeaway from all this is that Kp is the critical component for us to achieve control in this system. So by choosing the correct values for Kp, we can optimize our system. And there is some optimization to do that, to do there. So if Kp is too low, we don't ever achieve our set point. On the other hand, if Kp is too high, that might cause extremes in our control. So it might cause our system to oscillate beyond the safety limits of the materials of construction. And we look at some examples around that. So let's go back to our to the original formulation here. So we've done all this development, and then we said we want to find the values of Kp which give us good control. And we had noticed some of this before. So if you go over to notes, if you go over to linear system responses, that's notes 4, you'll find this section. So we had talked here about applying for our controller. We talked about applying a step input and a sine wave and so on. So if you look around, just looking for it. So if you look around here, around page 15, 16, 17, here's this example for a second order process. And we are applying step inputs and sine inputs. So for a step response, we applied different values of m. And in our problem, that's basically Kp. So for different values of Kp, we had different levels of response. And we found that we could get an oscillation, and we needed to control that value of m such that we limited how high that oscillation went. So that's what we are trying to do. We are trying to establish a criterion. Okay, my apologies for that. Can you all hear me? Okay, thank you. Okay, so if you read around this section, you'll see that we can look at how the system responds to different parameters. And for our second order process, when the ratio of our time constants is at a certain value, then we'll find the oscillation, we'll find that we get a certain level to our oscillation. We'll get a certain maximum amplitude to the oscillation. So we can limit the extent of that oscillation by controlling, by adjusting our controls parameters, right? And we will come back to this. There is a follow-on section. So after this section on implementing closed loop, on closing the loop, we'll find that there's a powerful way of investigating the plane of possibilities for Kp. So for now, we are just going to continue with investigating the plane in a kind of manual way. And I'm just trying to get back our simulation. Okay, so we can see, right, the main point is Kp is where we are going to achieve control in our process. And again, you can always come back to the time domain and really understand the process and understand how the controls are influencing things, right? So going back to our more formal way or this well-established way of investigating the plane, right? That was us going into the time domain and playing around with Kp. But we have in the Laplace domain this nice analysis that we can do. So first of all, we said that we can look up the roots of the system, and we can then understand how the solutions to this are going to show up in our time domain. So the solutions to this, in other words, the S values, remember behind GP and GC, it's a function of S. So those S values, there will be some set of S values that cause this equation to be true, right? So the roots of this, the S values of this equation are going to be the time constants of our time domain solution. And so by looking at those constants, we can figure out whether we are going unstable or getting oscillations and so on. So that's what we are looking at here. So right here, we have this is what we said we want to know about the roots of this. And in this particular example, if we had a first order decay, then we found GP is 1 over S plus 5. And we saw here that the root of this equation, there was just one root. You can see here there's only one value of S, which makes the 0, which is minus Kp minus 5. So just looking at this root, we can see it's always going to be a negative number. Remember Kp, our controller constant, we only vary that from 0 upwards. So we don't specify in the real world imaginary numbers for our controller. Our controller uses real numbers, which are always positive. So Kp being a real positive number, this is always going to become more negative. So we will only get S values which are negative and real. And so we can say that this is always going to be stable. So in our first problem, when we had a negative 5 for tau, we always found that this was stable. So even if we used a 1 here, right, the system just fell away towards 0. Didn't reach, not 0 in that case, but and then if we used arbitrarily high numbers for Kp, it was also stable. It was just constrained to some number. So for the exponential decay, we always have a stable behavior in this process, right? Sorry, I should be pointing here. For an exponential decay, we always have a stable behavior in our process. Now let's look at the unstable version of this. And here, this is all just a summary of what we looked at when we went into the solution just now. So here's the case. If we have a positive 5, so if dy dt is plus 5 times y, if you do the same development that we did for case A, you'll find a GP function of 1 over S minus 5. So in a plus 5y case, we get a minus 5 here. In a minus 5y case, we get a plus 5 instead. So anyway, in part B, it's S minus 5. And if you, again, apply that in this equation, you will find now that the root is at minus Kp plus 5. And this gives us a nice criterion, because it's telling us that if we want S to stay negative, then Kp has to be at least a 5, right? If Kp is less than 5, then S can have a positive real part. And that's what we saw earlier. We said when we used, I set that to 5, and if we use a KP value of 1, right? So let's look here. If we use KP is 1, then this is -1 plus 5, so that's a +4. So our root here is +4, and that means we have a positive real part, and that's unstable. Right, so go back to tutorial 2 after this and verify what we said there. We said if we have a positive real part, our solution is going to explode. And here, if we set that low value for KP of 1, you can see here the solution is exploding away. And here it's also telling us that the critical value for KP is a 5, right? So when S equals 0, KP is a 5. For S to become negative, KP must be more than 5. So let's try that critical value of 5. So below KP is 5, it's exploding away. For KP equals 5, you can see it's increasing, but it's increasing linearly, right? So this is not an explosion, right? We don't regard a linear increase as an explosion, right? So in this case, that's a linear increase. And then the moment we go above 5, let's just set 5.1, for instance. You can see a slight tilting here. And in fact, what I need to do is increase we can increase our limit here. So instead of 0 to 2, let's make it 0 to 200. And in fact, I want to come back to this 5. So it was only increasing there because we weren't at the steady state value yet, right? We said KP is our critical value, and we are trying to reach a steady state of a 3. So if we set that, we said we have that linear increase in KP, and then if we increase KP just slightly beyond the 5, then you can see it's bending that curve down and we are reaching a steady state. It's not the intended steady state, it's not the 3 we are looking for, but it's at least causing the system to be stable, right? And we can make this arbitrarily close to 5. So let's try 5.0001. If we run that, you can see we are getting closer to our linear response. So this is not an explosion anymore, right? It's not an exponential increase. Okay, so that's on the tuning of KP. So for an unstable process, we can bring that to a stable operation. And we can think of it as by implementing control, we are actually changing that process, right? We are introducing another flow rate and we are changing its value depending on the state variable. And so we have actually changed the dynamics of that process. That's the whole purpose of control, right? To change the dynamics of our process. Okay, so that's what we have for example 1. And here again, there's a bit more development if you want to derive those equations, and that links to what we were doing in tutorial 3. Now, what we want to do is, in a way, relax a bit about deriving equations, right? So we know that for some given process, we will get some transfer function GP. And so from now on, we will say, well, you can go ahead, derive your model, and then convert your model to the Laplace domain, and you will get some transfer function GP. So instead of having to do all those steps of deriving GP, from now on, we'll just assume a GP and say a certain process has a transfer function given by this equation, and then tell me the control parameters required to reach a given set point. Okay, any questions or comments so far? Okay, so there are a couple of ways to solve this, right? So once more, we want to find the values of Kp that will cause us to control these processes. So there are some different ways to do that. First off, we know that generally speaking, we have this relationship that the roots of this equation are going to tell us how the process will behave. So all we need to do is find that equation for these GPs, and we then solve for the roots. In other words, we want the roots of some version of this equation. And in fact, I'm maybe speaking a bit too mysteriously there. We want the roots of 1 plus GP GC equals 0. Right, so our GC in the case of a proportional controller is simply KP, the proportional controller is constant, and then GP depends on the process. So in question 2, all these examples are given. So we need to find the values of S that give us these roots. And we want to also specify the values of Kp that give us nice values of S, right? It's true that we can always find S as the roots, but we don't want S to be any value. So we don't want S values with positive real parts. We don't want S values with very strong imaginary parts because those give us strong oscillations. So we want to change the way this process operates so that the S roots we get are nice and well behaved, right? And we do that through Kp. So this is how we as engineers are causing control in this problem. We've added this flow rate and we are using this proportional controller and we are able to change this Kp value. So that's our handle now on nature, right? We are able to change how nature is going to respond, right? Everything happening in our reactor and so on, as unnatural as it may look, it's all about creating an environment for nature to behave a certain way, right? The intrinsic reaction rate prescribed by nature for these chemicals, that's going to behave as nature wants to behave. But we can exert our control over how nature, or what operating regions nature is going to stray into. We can control that by influencing this Kp value. And of course, we do that by changing the settings on our valve, on our little controller in that process. So we can exert a control action through this Kp, and that's how we are going to achieve what the behavior that we want. So we are going to look at the solutions to this equation in each of these cases. And in the code, the way I do this is, so here I've listed all those processes out. And so if you want to simulate any case, you just comment, so you can uncomment the selected one and comment in, so remove the commenting on any of those. And in this code, what it does is, so that's the only place you need to change anything, right? Because in the rest of the code, it will prepare the equation that we need. So we know that what we actually need is 1 plus Kp times that process. So we choose the string, and of course you can put in your own string as well. You're not constrained to any of these. So you can investigate any process. And what I'm doing here is using the symbolic solver. So of course, normally we would go and solve this by hand, so to say, but there is a nice symbolic solver, and that can find the roots of the equation for us. And then we can generate all the solutions that we'll get for different values of Kp. So this is how we can investigate different values for Kp. So up to now, we looked at just a single value for Kp. What we are doing here is generating a range of Kp values, and we are looking at what the solution is doing after that. And so you can read up in the code, and I think I wrote more notes for this in the solution. You can look at what all these things mean in the code. But basically, let's choose one of these problems. Let's just start with this one. So if our process happened to look like this, right? We've taken the model, we've Laplace transformed it, and now we have 1 over s plus 1 and 1 over s plus 2, and we are applying proportional control. Then we can solve it like this. All right, so if we just run this, so you see here it's looking up the solutions. So it finds 2 solutions so far to that equation. So yeah, there are 2 solutions, and it looks like this. And so it's saying that, so ignore these green lines for now. So it's saying that there's one root which starts here and moves up, and I'll explain just now why I'm saying it starts here and not there. But you've got a root that starts here, moves in. So when I say starts, that means Kp is 0. And then as we increase Kp, that root moves along this axis, and then it reaches a point where it starts increasing in the imaginary part as well. And then similarly, there's a second root which starts here, and it changes in its real part and its imaginary part like that. So you've got the 2 roots that move through the system like that. So we start with Kp like this, and then as Kp increases, the 2 roots move in and they cross and they go across like that. And the first thing to notice here is that the real part is always nice and negative, right? The real part of these roots are always less than 0. So here I'm plotting the imaginary part and the real part. I forgot to say that. So when I'm plotting a root, a root is generally speaking an imaginary number. And so we are plotting just the imaginary part against the real part. And we are getting different roots because for different values of Kp, we get a different value of the root, right? Because of course, this is our equation. In fact, let's look here. This is the root. So for different values of Kp, we get different values of the root. So our root is varying like this. So the first thing we can say is that this process is always going to be stable. It never has a positive real part. So our smallest value for Kp is a 0, which is here and here. And then as we go off to infinity in Kp, those roots just race off to minus and plus infinity in terms of the imaginary parts, and the real parts seem to stay at minus 1.5. Right, so it's always stable. It is more oscillatory, if you like. So as we go to stronger imaginary parts, then the real response is going to be a stronger oscillation. Right? Now, the point of these green lines here is that we had shown in, remember I said in notes 04, we had found a way to determine the amplitude. So remember our oscillation looks like this, and we had found, we had worked out a way to estimate the height of that amplitude. So as we use higher values of Kp, right? As you use increasing values of Kp, your solution will oscillate more strongly, right? Because remember, Kp is going to tell us how quickly our system will respond to a non-zero error. So if your set point and your current value, even if there's a moderate difference between those two, if you have a very high Kp value, then the control action is going to be very strong. So for instance, if you have a small temperature difference, but your Kp value is very high, then that system might be dumping lots of steam into your reactor, into the jacket at least. So the stronger the Kp, the stronger the control action. And you can imagine if this is temperature, a strong control action will cause you to shoot up very rapidly here. And then the moment the temperature goes over the set point, then it's going to be a strong negative influence. So it's going to jump down here. So you see, the stronger your control action, the stronger will be your oscillation as well before the system settles down to a steady state. Now, that is true, but at the same time, we do want nice, strong control action. So if we don't take very strong control action, it might take forever for us to get close to the steady state. And so we have to play this balancing act as controls engineers. We want strong control action, but we don't want it to be so strong that it's going to cause the process to bounce around all over the place. And we'll see later on that a good criterion for this, a nice balance between those extrema, is given by these green lines here. So these green lines are actually 45-degree lines, and you'll see why it's 45 degrees if you read back in notes 4 or watch the video for notes 4. You'll see that the 45-degree lines correspond to the first oscillation, right? The first overshoot here. And that first overshoot is basically giving us the maximum amplitude. So where you have that maximum amplitude, you can estimate your amplitude ratio, and that basically lets you constrain yourself. So you can say, well, I can see Kp is 0, Kp is 0.10, Kp is 1, 2, 3, 4, 5. Okay, so Kp is 5 here. So where I intersect with this 45-degree line, I know it doesn't look like a 45-degree line. That's just because of the scale here, right? Well, actually, the scale looks fine. No, this is 0 to 30, and this is 0 to 2, right? So it looks flat. Those green lines look flat, but those are actually 45-degree lines. So where the root intersects with the 45-degree line, we'll find a Kp value, which gives us a moderately decent amount of oscillation. So the oscillation won't be so bad that we are out of control for a different reason. And at the same time, it will be strong enough control action that we get a reasonably timed control response. And we'll come back to this when we reach the frequency domain dynamic, when we reach the frequency response part of the course, we'll come back to exactly why that is. So that's what we can look for in this root finding. We need to plot out our roots, and then we look at those roots and we look at the regions. So the first most important thing, do we have Kp values where our real part is positive? If we don't, then we can say the process is always stable. Or if we do, then we say, well, then we must stay away from those Kp values. And in fact, maybe it's useful to put in the problem we were looking at just now. Let's put in our first order explosion. So it was 1 over s minus 5. And this needs to be a string. Okay, so if we run this, we can see here, and it's not so easy to see. Let me just limit how far Kp varies. Let's make this between 0 and 10. Yes, no. So when Kp is 0, we are starting here. Okay, later, thanks. Okay, sorry. So when Kp is 0, our root is here. And then as Kp increases and reaches a value of 5, then we reach a 0 here. And then beyond that value of 5, we've got negative real part. So in this case, there's just one root. You can see the single root being plotted here. And we can see we don't want this part of the domain. So we don't want these KP values. So from here on is good enough control. And you can also see these other plots down here. So in these other plots, I'm showing the real part and the imaginary parts of the solution. And we are showing the complex conjugates of those. So we are plotting here as a function of Kp. So as Kp varies, you can see here the real part. So for Kp of 5, we start to go to negative parts. So that's how you can use this. So this code is, if I say so myself, it's quite useful. You can use it to investigate any process, and you can plot out, you can investigate different controller settings. Okay. Any questions or comments there? Okay, so that's what we have for using the code and finding roots in that way. There is available from the field of complex analysis, there is available a nice way of working this out. So if you don't want to do it as code, if instead you want to use root locus plotting principles, then there are these nice observations that you can use to sketch out your root loci. So we can say that your root locus will start at Kc equals 0. So you've got a couple of different solutions, and then if you set Kc equals 0, then you can find those initial values, and then you can look up, so as Kc goes to infinity, it turns out that the zeros of your open loop transfer function, those are where your roots tend to go eventually, and we'll look at some examples. And then the number of loci equals the number of poles. And you've sort of been seeing that just now. When we did that first order lead case, we had just the one root crossing. And then when we looked at the case 1 over s plus 1 and 1 over s minus 1, we saw two different roots moving around. Those were doing that. You always get complex conjugates, so your complex parts of your roots, so your roots always show up as complex conjugates. And then there exists a so-called center of gravity. So if you look at your roots, there will be a point you can identify, and your roots kind of radiate around those points. So the center of gravity is a useful point in sketching out your solution. So you've got your starting points, you've got a center of gravity, and you've got asymptotes. And all that is quite enough to sketch out a solution. So without solving for each point using code, you can use these 5 principles to draw out your root locus plot. And we have an example of that here. And I'm just going to check on my power source here. Okay, so taking this s plus 1 example, yeah, it's probably a bit easy for you now, but we've done a similar thing already, right? We've already looked at s plus 5 instead of s plus 1. So, well, I guess here we are doing it using this root locus sketching approach now. So first, yes, we know that when Kp equals 0, we can see that the root starts at a value. So in fact, let's also look at it here. So we set here Gp equals 1 over s plus 1. then let's just set a small value for Kp. So let's say 1e minus 3. So if you plot that, you can see that our root is starting, well, we can't even see the roots. So if Kp is 0, then it's minus 1. So we can see that directly. We start at minus 1. So yeah, the root, I guess, starts somewhere here. And it starts at minus 1. And then as Kp goes to infinity, if you look here, when Kp goes to infinity, that infinity makes that minus 1 infinite. It makes it's small in comparison. So S becomes approximately minus Kp. And so you can, that's how you work out the asymptotes, right? So in this case, when Kp goes off to infinity, then we can neglect the minus 1 as being very small in comparison. And then it's just going off to minus infinity. So S is pointing in that direction. So that's how you find the asymptotes. You find the starting point, and then you imagine if Kp is going to infinity, in which direction is my solution pointing? So that's there. And then the number of loci equals the number of poles. So in this case, we have just one pole, right? There's just one solution to this denominator. And so we've got just one root that will appear. And you can think of this code as being the experiment that you can use to verify what we are saying. So in this code, when you do run this, you'll find just the one solution pointing out. So that agrees with these principles. Yeah, so this case is kind of too easy. Let's take a more interesting case here. So if we have 0.5 s over s plus 1 and s plus 2, then clearly we want the roots of this equation. And maybe we didn't spend enough time emphasizing this. We always take 1 plus GP times GC. In our case, GC is KP, right? For a proportional controller, GC is just equal to KP. So we multiply KP here, and then multiply by GP. So so it's that, and then 1 plus that equals 0. We want to know about the roots of that. And then we just multiply both sides by that denominator, so it looks like that. And then we can say, well, so we can just go ahead and look for roots of this equation. So the roots of this equation can be sketched by first finding the centroid, right? So there exists some point around which your asymptotes are going to radiate. And so your center of gravity is going to be given by the number of poles minus the number of zeros. The actual sum of the poles, the values of the poles minus the values of the zeros, divided by the number of poles minus the number of zeros. So here we don't have any zeros. We've got the two poles. So you've got -1 and -2, and we've got n equals 2, so it's -3 over 2. So that's our center of gravity. And then the angles are spaced like this. So it's 2k plus 1 over n minus m times pi. And we are looking at k values going up to n minus m minus 1. So in our case, n equals 2 and m equals 0. So k is only going to be 0 and 1, right? N equals 2 minus 0 minus 1. So this becomes a 1. So when we write the sequence, we only go 0 and 1, right? So k is 0 and 1. So once more, to find the angles of our asymptotes, we look at k in this range, k as this set of numbers. So you look up the end number first. So in this case, n equals 2 and m is 0. So this is 2 minus 0 minus 1. So that's a 1. So you follow the sequence. So you've got 0 and 1. So those are your 2k values. And so you can say that your angles are going to be 2k plus 1. So when k is 0, then this is 1 over 2. So 1 over 2 pi. And then when k is 1, this is 3 over 2. So 3 over 2 times pi. So those are the two angles of your asymptotes. And then, in fact, that's enough information to start drawing this out. Right, remember, when Kp equals 0, you're going to get S equals -1 and S equals -2. So you'll start with -2, -1, and then you are going to get angles 1/2 pi. So 1/2 pi is pointing straight up, and 3 pi by 2. So that's 1/2 pi, that's a pi, and that's 3 over 2 pi. So one is going to do this, and one is going to do that. Right, so that's how you draw these things, and if we just apply it in our kind of experiment here, in our numerical. I'll try and fix my code for this, but yeah, like we saw earlier, we had the two roots that, and we found that the one root was going up vertical like that. So we found that the centroid, remember, so just looking at what we've worked out here, we said that there's the center of gravity at -3 over 2. And so you'll find that when the two roots move in towards each other, you can imagine easily a point which is at -1.5. And then you have the one root shooting up that way and the other root shooting down that way. So you can see that they are kind of symmetrical around that -1.5. And then we found the one root was at pi by 2. So the one root moved in towards the centroid, and above the centroid, it moved straight up like that. And then the other root moved in from -2, and then it reached the centroid and it fell straight down. So you've got the two roots like that. And then we have the 45-degree line. So we find the Kp value where the root crosses the 45-degree line. And then that tells us a desirable value for Kp to control that process. Yeah, here, well, okay, I was trying to run it, but it's here as well. So like we said, the one root was at pi by 2, and the other one at 3 pi by 2. And so all we need to do is find the value of Kp, which crosses this value. If we look here, it's around a value of maybe 1.7, something like that. So we can use these other plots here. So here we are plotting the real and imaginary parts as a function of Kp. You can try and figure out which root we are looking at. Remember, we've got two different roots to look at here. So you've got two different roots being plotted here. And in this case, this root is starting from a low value. So the real part is starting from a more negative number and going more positive. So it's this root, right? And in fact, it's in order. So it does this root first. So this is the first root. And so that's this plot. And you can see here that the imaginary part of this is going to cross here at around -1.7. So your -1.7 is somewhere here. And so we can read off a Kp value just by projecting down here. So that's something of a challenge of this section, right? You have all these different plots to navigate. We will look at more efficient ways of navigating the plot and finding controls values more cleverly. So there are some other methods we are going to get into which make it much easier to navigate this plane. But for now, please do understand how to work with the root locus diagram. So first off, we are plotting the imaginary part and real part of the roots of that equation, right, of 1 plus GP GC. And so these are the roots that make that equation true. And behind this root, behind this set of values, right, each curve here corresponds to a specific value of Kp. So we've got two roots, so we'll have two values. So every time we choose a kp value, so if we choose kp is 10, that might be on this root, there'll be one value here and there'll be another value here. As we increase kp, that's changing the roots, right? And we'll reach a kp value where we are crossing this 45-degree line. And we'll see later on that that point gives us a reasonably well-behaved system, that you do get oscillations, but they're not so bad and the process responds fast enough. Okay, so it's something that you have to spend some time thinking about. And here, when I'm plotting this root out, right, this is one root. So just the single root, or just this single root, is being shown here. So root 1, I'm showing the real part as this blue line, and you can look up the real part. You can see here, in terms of the real part, this is starting at -2, so the real value is -2, and then it increases to -1.5, and then it doesn't increase beyond that. So it reaches a -1.5, and you can see that here. It starts at a -2, it goes up to -1.5, and it stays on that. And then in terms of the imaginary part, it starts on a 0. So you can see it starts on a 0, and then it becomes more negative. So it gets more negative like this. And we had said it looks like it's crossing around maybe -2 or maybe 1.5, something like that. So we can look up where does it cross. So it's crossing the root here, and then we can read off the kp value and say that's a reasonably good number for our controller. Right, so that's how you use root locus diagrams to design your control system. Any questions or comments there? Okay, if not, then I'll leave you to practice this a bit further, and I'll release tutorial 5 during the week as well, and then we'll have another session to go through that. In the meantime, you can also email any questions, and it seems like we'll have 3 different videos. I'll try and put them all together and get that uploaded. Thanks very much.